Okay, good afternoon, everybody. Thank you for joining this session about reinventing Malditov applications in clinical microbiology. I'm Belén Rodriguez from Madrid, Spain. I have the great pleasure to share this session today with Professor Idelevich from Germany. As you know, Malditov for quite a long time has been in our lives and in our laboratories. So the first goal was to implement it for identification, but luckily we don't want to stop by that, by using it as an identification tool. We want more, and we don't want to forget the great potential of Malditov. And luckily, there has been a good number of abstracts submitted for this ECMID about this topic. So we will present today just a good example of a great project. It's a pity that these sessions are so short because there were so many other abstracts to show here. So the first one will be presented by Dr. Park from Sijin Medical Foundation in Seoul, South Korea, about subtyping carbapenem-resistant Enterobacteriaceae. Dr. Beck, thank you for being here today. The floor is yours.
Okay, thank you for the introduction. I'm Jaehyun Beck from South Korea. I'm a little bit nervous because this is the first time attending this conference. And I'm not a microbiologist and not clinician. I'm just a protein biochemist using mass spectrometry. I came from the South Korea, a small country, but I want to share our results. And I really appreciate let's give some opportunity to share our listen to work. Okay, do you like beer? I'm going to start with this one. How about this? This is just a pattern of the spectrum. I love this beer, Stella Artois. And how about you? And this pattern is from this yeast culture, and probably this is a glycan, carbohydrates. So that's why I realized why I'm getting a fat on my belly and waist. Are you too? Okay, Malditov is, I think, really fast, easy and simple one. So that's why this society, you guys use for bacterial identification and other stuff as well. So I would like to remind this slide to share what the mass range is important for the antibiotics degradation under 500, for the bacterial ID to 2,000 to 20,000. But in my case, for the direct identification of a CP molecule, normally we use 12 to 30 kilodalton. So which is really challenging because this is in terms of low efficiency of ionization and huge mass errors. So beyond the bacterial identification, we want to see more near horizon. So for example, I want to see, figure out which bacteria has good mind, bad mind, or strong enough to fight antibiotics using something other stuff. So we want to put effort in accumulating the highest accuracy, sensitivity, and reproducibility. So just as I said before, there's intrinsic limitations in Malditov mass, specifically in this high mass range, such as low sensitivity in complex samples, and low mass accuracy, low ionization efficiency, and low reproducibility. So that's why we accumulate our solutions for last couple of years. We accumulated this evidence based on our publication, just like here. And first of all, I would like to mention about the purification stuff. So we use the osmotic lysis to get some partial or fraction, and this is really contribute to the higher sensitivity. And And next one is we introduce the internal calibrator for the protein analysis to increase the mass accuracy. The last one is I want to share a little bit. We developed a new plate which has a graphene layer on our semiconductive plate, which is really good to give a high reproducibility in mass and intensity from our targets. But I'm not going to cover this topic today. But I'm going to share today OS MALDI and A MALDI. A MALDI is advanced MALDI, which has a higher mass accuracy and sensitivity. So you know that osmotic shock is really common way to open a membrane. And most of the carbapenems are located in a periplasmic region and between inner and outer membrane in gram-negative bacteria. And we want to open this one, and then we got a partial purification upon this process, simply detect this KPC protein. So to get more information, we did some comparative analysis using the bottom-up and top-down analysis upon this osmotic lysis. So as you can see here, the red dots, the periplasmic protein is really enriched in the supernatant fraction of OS lysis. And also measure the top-down analysis, we can compare the abundance also enriched in supernatant of OS lysis. And then we optimize this process based on the different concentration of salt. And then we finally got the really high sensitive spectrum on MALDI. So to increase the mass accuracy, we introduced the intrastandard KPC protein. At the C-terminus, we added out the histidine, 6 histidine there, which allow us to add it up to 822 Dalton. So based on that, we can recalculate our mass. So boom, you can see, wow, nice mass calibration. And probably you know that on the multiplate is really heterogeneous crystallization is effect to the mass errors. We applied to another the beta-lactamase, GS, CTX, BIM, IMP. That's okay, just like a KPC2. And also the next topic is we optimize the all kind of parameters such as Maltitop and the sample preparation. So we increase the sensitivity. We control laser power gain and number of laser shots. And also we switch it to the synaptic exit as a matrix. And also we use the sandwich way. So you know that matrix, sample, matrix. So I'm going to talk about a little bit about 2 tests. The first one is analytical performance test. This is a following series guideline. And we selected 12 KPC positive and 12 negative strain. And to get this 360 point data point from this experiment, 300 persons, 10 days, 12 positive or 12 negatives. So determine the noise level, we got this kind of density map. And this red line here is the noise, and from negative, and blue line is here is a signal from a positive. So we can determine the threshold like that. But in case of A MALDI, we increase the sensitivity and also decrease the noise. So we have a substantial separation. One order the gap is really nice, and one order of magnitude. So which is really good. So next topic also the clinical isolated, same thing, increase sensitivity and a little bit overlap the OS MALDI, but in our A MALDI, so really nice. So I want to share this, the final results. All kinds of the carbapenems are really nicely detected. And this is one example of a KPC spectra and PCR results, and NDM, OXA as well. And I'm going to a little bit deeper to see the subtyping, the KPC2, 4, NDM 1, 5, and 8, OXA 48, 181, 232, and GS5, 24. So this is really good, also same spectra here. So those 2 guys, KPC2 and 4 has just a 10 Dalton mass difference, but OXA, in case of OXA, has a up to case a little bit 50 or the 100 mass Dalton difference. And I'm going to share this slide on the right side. This is a molecular mass distribution. You can see there each isolate subtypes can identified within 10 MOG value, except NDM case. NDM has a has the covers each other. So on the left side, you can see Venn diagram. There is some overlap between KPC2 and OXR, and NDM, KPC, OXR, NDM. So this is from the tertiary nursing hospital. So I want to share this typical example. The simultaneous detection, OXR 181 and KPC2 in same strain from one patient. So I'm going to share this slide as a summary. We have an outstanding performance at higher mass range using A-MALDI, and we can be subtyping or majority of these carbapenem images. Also allow us to do something more in epidemiology studies and something others. And probably this technology also used for another on clinical unmet needs case beyond clinical microbiology. So here is my thankful people. I really love this picture in the left top because there is some halo behind me. And this is our last picture slide. We want to do something more using MALDI. So probably I can do so ASD free. So we calculate this amount based on our internal standard. Probably this is going to be really great. So we did something more. SMS data is supported our evidence. QMALDI, the quantification result is pretty good. So we can see something, this bacteria has a sensitive or the negative, resistant, based on the amount of KPC2 abundance. That's follow the ASD result, I think. Thank you for your attention, and for you, I am open to get a question you might have. Thank you.
Thank you very much for this really nice presentation. If there's a question from the audience, we have, okay.
Jaroslav Rabák, Czech Republic. Congratulations for excellent results. I have a question. So which matrix have you used? Because 10 years ago we published very similar methods with osmotic lysis as well. We patented it. And also, have you seen double-charged ions in your spectra? Because sometimes it can help to distinguish in exact molecular mass.
So for the first question, we normally use the synapinic exit rather than CCA. Yeah, that's better because we study a lot and optimize things. And what was the second question?
No, if you have seen this, we also used, and if you could see double-charged ions in your spectra, because sometimes it can help.
Okay, so probably I can say it like this. The CGCA is give a higher sensitivity, but give a lower resolution. So if we distinguish in mass, this assay is better. Another answer is if we look at the addition of our target molecule, because assay is sometimes added up to our target molecule, so that's why we make some other picks there. But we can measure the exact mass upon our internal standards. That's okay.
Thank you.
Yeah.
Thank you very much. So we don't have time for questions now, maybe at the end of the session. So the second speaker is Professor Hrabak from the Czech Republic, from the Faculty of Medicine in Pilsen, Charles University, and he's going to show about the detection of other targets.